So if you are watching this video, you are starting off on the second semester of AP Statistics. And honestly, I enjoy the second semester of AP Stats even more than the first semester because there's a lot of really good stuff that we learn about in this half of the class. Things like confidence intervals and margin of error, things like significance testing, how you actually decide if results are statistically significant or not, rather than just eyeballing them. We get into other good stuff like chi-squared distributions and all this other like awesome content right here that you will actually use all the time if you do research later on in your life. Very, very useful hands-on stuff. Before we get to all of that though, we need to build a little bit of a foundation because we're jumping into new, never before stuff you would have no familiarity with at all here in your math careers. So this chapter 7, builds up the concept of a sampling distribution, which is something we're going to start talking about in this lesson here. I think chapter 7 is one of the two toughest chapters in our book, along with chapter 6, which we just finished. So these two units are historically the toughest for kids overall. The reason for that with chapter 7, when we get to May and you're looking back on the year, this won't seem so bad anymore, but it's just so different and so new that it's going to feel just like a ton of stuff that you have to kind of soak in this unit here. The good news is once we learn the stuff in this chapter, we actually see it again in chapter 8. We see it again in chapter 9 and again in chapter 10. So by the time you see it in these different cycles here, it's going to feel totally fine. But it's a lot to take on at first. This chapter is also probably the shortest in our book. Counting this video, there's only going to be 4 videos in this chapter. So it's a lot of content packed into just 4 lessons, which can be a good thing and a bad thing. It's good because it's less to study and you can really practice this stuff to make sure you understand it. But it's bad because if you're not careful, this will just sneak up on you when we have our chapter test here, and it could be something where you didn't understand it as well as you thought you did. So definitely be on your toes in this chapter. It's a lot to take in, but we will practice it and you will get stronger with this material as time goes on. So yeah, with my little summary out of the way there, let's jump in and learn about the concept of a sampling distribution. First thing I've got for you guys here is the kind of a difference between 2 vocab words, and I believe I've used this vocab with you guys first semester, so this shouldn't be like totally out of nowhere, but the difference between a parameter and a statistic. So the parameter is the true value of whatever you are looking at in the population. Okay, so the parameter is the actual true value of whatever you're looking at. That could be a mean, it could be a median, it could be Q1, it could be the standard deviation. It doesn't really matter. Just whatever you are looking for. The true actual value for the whole population is called a parameter. In contrast to that, we have the idea of a statistic, and the statistic is going to be the estimated value for a parameter based on what we got in our sample. And it's going to be pretty easy for you guys to keep these things straight. Parameter and population both start with a P. Statistic, sample, both start with an S. So it's very easy to keep them straight. The parameter is the answer for the whole population. The statistic that you get is what we got. It's like the answer for our sample that we use to apply to the population. This class is called statistics because most of the time in real life, we don't know the population answer. We use our statistic, our answer from the sample, to try to make predictions or estimates about the parameter. There are going to be 3 big kind of topics or ideas or variables that we worry about this semester. We kind of focus on a couple and get really good at them. One such variable is the mean. And when we are talking about the mean, there's going to be a different symbol for all of these things, whether it's a parameter or a statistic, and we've used these before. So let's say I want to know the average ACT score across the entire country. That's a known quantity. I believe it's like 21 point something nowadays. So 21 is the national average. It is the actual population mean. The symbol we use for that is mu. So we've got mu as one of our big parameters. That's for the population. But let's say I took a random sample and I have like 1,000 people and I average their ACT scores. I get like 22 or 20 or 21 or whatever. Well, that is my sample mean. And we use the symbol X bar for that. So same concept, it's an average, it's a mean, but different symbol based on whether it's a parameter or a statistic. There are going to be two other values that we use a lot. The next is standard deviation. And as you will recall, in the population, the parameter is sigma, and then we use S, or S of X, in the statistic version of that. We have one other thing we're going to use a lot this semester, which might be new. I don't know if I've talked about this yet, which is going to be lowercase p right here. Lowercase p stands for the proportion. And when I talk about a proportion, basically I mean a percentage. So I may want to find the proportion of people in America who wear glasses. Or I might want to find the proportion of people in the state of Missouri who want to vote for such and such a candidate. So anytime you're looking for a percentage of something, the variable we use for that is p. The statistic version for p is going to be p with a hat on it. So p hat is our sample proportion. P is our actual proportion. The other two use Greek letters here. So we have mu and we have sigma for these two. The Greek letter that goes along with this is actually pi, but pi is used so many other places that like we don't bother doing that. So we don't use a pi and a p. We just go p and p hat and kind of break that Greek letter trend that we've got going on. So yeah, big difference there between a parameter and a statistic. So let's practice these with a couple quick examples here. So this first one I'll talk about to get with you guys here, and then I'll have you try the second one yourself. We are going to identify four things. What is my population? What's the parameter that I care about? What's my sample? And what's the statistic that I care about? Those four things for this problem. And in a Pew Research Center poll, Pew Research is a very famous data collection company that do a lot of surveys. They asked 1,102 12 to 17-year-olds in the US if they have a cell phone, and 71% of them said yes. So let's think about let's start with population. The population that I care about, what group am I trying to collect data on? Well, that's going to be all of the United States. Everybody that I talk to is in the US. Presumably that's all I care about for this problem. So my population is going to be, and it's all 12 to 17-year-olds in the US. That's who I'm trying to collect data or find out the answer about. That means my sample, which again, I'm going to define the sample in words. The sample is talking about the people you actually got data from. So it's the 1102 12 to 17-year-olds selected. Okay, we've done this like back in chapter 1 where we talked about the population, we talked about what our sample is. Nothing crazy or new there. What we're going to add on to here, though, is talking about the parameter and the statistic for this problem. So the parameter is what I actually, like the value that I care about for the whole population. In this problem, we are looking at what percent of people own a cell phone. So it's a percentage problem, and our newfound variable for that is going to be p. So our parameter is going to be p, which is the true proportion of 12 to 17-year-olds who own a phone. Okay? So it's the actual percent in all of America who own a cell phone. That's p. And then we have our statistic. So our statistic in this problem is going to be p hats, which is our value, actually, that they gave to us in this problem. This 71% applies to the 1102 kids who were in the study. So p hat is 0.71. It's our percent from the sample. P itself, we don't know. We're trying to figure out P or estimate real P using p-hat. That's the idea of a parameter in a statistic. So I'm going to pause myself and then write down answers for this one at the bottom there, but you should do the same. So pause me and try the second one for yourself, writing out those 4 things. All right, so I'm back here with a little sample answer here. A couple quick comments. As far as the population goes, it says in the problem that the pediatrician picked 50 of her patients. So it's not super clear. Is she trying to figure out the height of like all 10-year-olds? Is it just in her state? Is it in her country? Is it just out of her patients? They're not specific enough with that to know for sure. So whether it's all 10-year-olds or just all 10-year-olds who are her patients, that's kind of just unclear based on the wording. The sample is easy. It's the 50 that she actually selected. In terms of parameter and statistic here, we have those big 3, mu, p, and sigma, that we're going to spend pretty much all of second semester analyzing. That's not to say that we can't ever do stuff with things like Q3 or just random other stuff out there, but it's just not going to be a focus for us. Not that you can't do research on them. So if you have just a random variable, it's like, how do I do a symbol for this? Like if what I ended up doing is I did Q3 for the actual parameter and I did Q3 with a hat on it for the sample. And the sample had a 56 for the Q3. We don't know the actual Q3 for the population. So that's the idea with this vocab, and it's not so bad once you practice it a little bit. Let's go ahead and move on and talk about the concept of sampling variability. The idea behind sampling variability is that different samples from the same population can produce different values for our statistic. So what does that mean? Let's go back to my ACT example from earlier. Let's say the actual average in the state of Missouri is a 21 on the ACT. I could take a sample of like 50 high schoolers in the state of Missouri, and I could get, oh, my average is 22.4. You could go and talk to a different 50 people. You could be like, no, I got 21.3. Somebody else could get a 19 or a 27. So there's going to be some difference between your version and my version, even if we're pulling from the same population. That's the idea of sampling variability. It doesn't mean that you or I or anybody did something wrong. It's just kind of common sense that if we pull different samples, we might not get the exact same answer for our mean or our median or our standard deviation or whatever every single time we do it. Why do we care about it in general? Well, we want to make sure we're making good predictions. We need to know how much we can expect things to move around so we can account for that when we make our predictions. If I got 21 and you got 24, is that like a pretty even spread for where things are going to be mostly between a 21 and 24? Or could you get a 28? Could you get a 15? And ideally, we want that variability, like we've talked about already in this class, to be as small as possible. So there are a lot of ways, there are different things we can do to make that happen. But that's the idea behind sampling variability. Now, this next slide right here, super important. Lots going on here. So I got to break this down and talk to you about what's going on. But this is a really big deal, important slide. It is going to introduce the concept of a sampling distribution. So first thing I need you guys to do is look at my first bar graph right here. This bar graph is for my population. It is the distribution of my population. And I've got like a box with 200 like poker chips or whatever you want to call them, marbles, whatever in them. And out of those 200 marbles, 100 are blue and 100 are red. We are interested in looking at what percent of them are going to be red, okay? So in our population, very obviously, the percent that are red, which it says right here, is 0.5. 50% of the chips or the marbles in this box are red. Okay, so that's pretty straightforward. That's our population. Then what's going to happen is we're going to take turns picking samples out of that box of 200. We're picking samples of size 20. So I would go into that box and I would scoop out 20 marbles and I would look at how many of each color I got. Then I'd throw my marbles back in with replacement, and you'd come up and you'd pick 20 marbles out of that same box, and then another person would, and then another person would, etc. So looking at the second column, we are now looking at the distribution of sample data. So a sample distribution. So this is like my pick right here. I picked 20 marbles out of this box, and I got 8 reds, 12 blues. So that makes my sample proportion. So I wouldn't be able to see in the box. I don't know what's in there. I just picked my 20. And when I pick my 20, I get 8 out of 20 to be red, which is a 40%. So I come away thinking, oh, 40% of that box is actually red. The box is like hidden from view. So what's going to happen with that 40% is we would have like a class graph. And what I would do is I would put a dot at a point 4. Oh, I got 40% for my red. And my job is done. Then it would go to you. And in your sample, you're right here. You picked 11 reds and you picked 9 blues. So you came away thinking, oh, cool. The percent for red is 11 out of 20, which is a 55%. So you would come over to our class graph and you would put a dot right there at 55%. Your next classmate would come along. Oh, cool. I got 13 reds out of 20, which is 65%. So they would walk on up and they would put a dot right here at 65%. And we would basically do this again and again and again. And we would just keep on picking samples. Each time we did that, we would put a little dots at whatever we got for our sample. So obviously the values in the middle here end up being more popular and then less so as you go further along. The penny activity that we may or may not have done in class when I'm talking to you about this, normally I have kids collect pennies. Like we do that thing with the penny box. If you've done that, we were building this kind of a graph, except we were taking an average of penny years. But in our problem right here, we would be building this picture. This picture is a sampling distribution. So we have the population, what's in the full box. We have our samples. Our samples are what we got from one pick. And then we have a sampling distribution, which is built from repeated picks from the same population of the same sample size. We were all picking 20 marbles at a time when we did this problem, okay? So let me actually define a sampling distribution. A sampling distribution is a distribution of all values a statistic can take over all possible samples of the same size. It's the distribution of all different values and how frequent they are that a statistic can take over all possible samples of the same size. So basically, we would sit there and we would keep on picking 20 marbles at a time, putting them back each time until we've gotten like all the possible combos possible. We did something with the pennies. We didn't get a full sampling distribution right there because there's just so many pennies in that box. But that again is a sampling distribution. We take an average, we take an average, we take an average. Here, we're taking a percentage. We're taking a percentage over and over. So repeated sampling yields us a sampling distribution. And we will talk a super ton more about these. It's like the focus of the chapter, sampling distributions, but you need to be able to wrap your head around what is actually going on there. Each dot in a sampling distribution is a different sample. One of those dots is mine, one is yours, one is your classmates, etc. It's a different sample for every single dot. Now let's look briefly at this picture that we just came up with here. Notice that in the actual box that we couldn't see, 50% of the chips or of the marbles were actually red. And 50% was the most popular option right here. But a lot of people got pretty close to 50%, 45, 55, etc. Not too many people got like 15% or 80%. And if you look at the basic shape, this is a little bit foreshadowing here, but you can see that what it appears to be going on is that our friend the normal distribution will eventually be coming up again in this chapter, which is a useful thing. But that's what a sampling distribution actually does. So we're going to practice on a much smaller problem. There were like 200 poker chips in that last problem. That was going to take forever to build the whole sampling distribution. Now we have a population of just 4 numbers. There are 4 of them: 68, 71, 72, 75. That's our population, which is comically small, but it's basically just to illustrate what's going on right here. If I wanted to know the true population mean, I would average those 4 numbers and I would have my answer. But what I'm going to do instead is build a sampling distribution to illustrate how that works. So what I would need to do, if I wanted to make a sampling distribution, they have to tell me what I'm making the sampling distribution for. Last time it was the sample proportion. We looked at our percent of reds. This time we're making a sampling distribution for the sample mean X bar. So we're making a graph for our X bar. They also have to tell you what size your samples are going to be. And our samples are going to be of size 2. So we're going to write down all possibilities for what we could get for our average with size 2 samples. So it could be that I pick the 68 and the 71. If I pick those 2 numbers, that's a 69.5 for my first value right there. So that's one value for X bar. I came away, oh, my sample mean is 69.5. But you might have picked the 68 and the 72. Well, if you did 68 and 72 and you found the average, you come away thinking, oh, the average is 70. And then our next friend would come over. They picked the 68s and the 75. And that I think is 71.5 if you find the average. So that's what they think it is. Then we got somebody else who comes away with 71 and 72. They're like, oh, it's 71.5. We got 71 and 75. They think it's 73. And then we have one more, 72 and 75. They think it's 73.5. So we're going to make a little dot plot right now for all of our different sample means. So my smallest is a 69.5. So I'm going to go 69, 70, 71, 72, 73, 74. So I had 69.5. That was mine. Then you got a 70, so there's your dot. And then the next kid got a 71.5. And then somebody else also got 71.5. Somebody got a 73. Somebody got a 73.5. That is the full sampling distribution because there are 4 numbers in the problem. So it wasn't that big of a deal. If there were like 200 numbers in the problem, we'd be here for the rest of our lives writing down all the possible combinations and it would just be awful. So when we have big data sets, what we'll usually do is use a computer to help us build a sampling distribution, or at least an approximate sampling distribution. So yeah, that's how you make one of these things. And we'll learn why they're so useful as we keep on going through this chapter. We got another vocab word though for right now. An unbiased estimator. Kind of says what's going on with this word right here, which we've talked about. Remember that bias means you are unfairly favoring one side over the other. So an unbiased estimator doesn't favor one side over the other. That's like an unofficial way of saying that. The actual, like what the book will tell you, is that the unbiased estimator, a statistic is unbiased if the mean, I'm going to underline mean, if the mean of its sampling distribution equals the true parameter. So my dots are gone from that last page, but we had like those 6 dots. It was like this or something. If I were to average all 6 of those dots, take all of our answers and average them up divided by 6, that should get me the overall average of all 4 of those numbers if it was an unbiased problem. So if you have an unbiased estimator, when you average and find the mean of your sampling distribution, you should get the actual value you were looking for. Going back 2 slides to an easier example, so let's go back to this guy. If you look, the actual parameter was a 0.5, and our sampling distribution, the mean is like the balancing points. It perches right there in the middle at a 0.5. So this is unbiased. We aren't always going to hit 0.5, but we're not favoring one side over the other. If I were to take a very similar graph, let's say the answer is still 0.5 right here, but my picture went like this instead, so I was mostly over a 0.5, well, that would be a biased estimator. And obviously, we want unbiased over biased. Unbiased is good because it means we're not favoring one side over another. So yeah, let's go ahead and talk about these next 2 questions right here. And I have a really good analogy that I read from another, like a statistics author online. So it's not my own unique idea right here, but it's really, really helpful, I think. So what I want you guys to picture is a giant tub of super awesome ice cream. So we've got a big like swimming pool filled with like a rocky road ice cream. So we got all sorts of stuff going on in this ice cream. We got vanilla base, but then there's going to be chocolate fudge stripes in there. There's going to be caramel. There's going to be like nuts if you like those, marshmallows. Like there's all sorts of awesome stuff going on in this ice cream. Okay, peanut butter swirls, everything you could think of is in this ice cream. But you can't see inside, so you don't know what kind of ice cream it is. You just have this giant tub of awesome ice cream. Okay? That tub is our population. So let's say you took like one of those tiny little taster spoons, like you get at Baskin Robbins or wherever, and they let you try the ice cream to see what you get. Well, when you take your tiny little spoon and you put it in that giant tub of ice cream, and you can't see what's in there, you may come away with part that's just vanilla. So you're sitting there thinking, wow, this is a giant tub of vanilla ice cream. I might put my spoon in there, and I get on my tiny little spoon just peanut butter. So I think it's a whole tub of just peanut butter ice cream. Somebody else gets fudge, somebody else gets a mixture. So basically what's going on there is there's a lot of variability between your spoon and my spoon and their spoon and so on. That's bad. We don't like to have lots of variability because then we're all sitting there pretty confused, or not even confused. Like you think it's chocolate, I think it's vanilla. We're like not thinking the same thing. We want to be on the same page. So if you have a really small sample, it's very difficult to be like consistent in your estimates. If we're going to look at the average ACT score in Missouri, but we're going to talk to 3 people and average their scores, well, shoot, I picked 3 kids who are in AP stats, and my average is crazy high. Wow, it's like a 26, 27, 30, 34, whatever. I think the average is really high. Where if I take a sample of a couple hundred kids, I'm going to get closer. I'm going to get a mixture of everybody, and I should get closer to the actual answer. Going along with my ice cream analogy right here, instead of taking those little taster spoons, what if I took like an actual ice cream scoop, or I took like a bucket of ice cream? If I do that, the chances of me getting just vanilla or just chocolate is a lot smaller. What I'm going to end up seeing is a mixture. And if I have a mixture in my bucket right here, and you take your bucket out, our buckets are going to look pretty similar, which means that there is low variability between my sample and your sample. And that's a good thing. So how can you reduce the variability of a statistic? Meaning, how can you make sure that your result and my result are similar to each other? You have to increase the sample size. If you increase your sample size, my result and your result should be fairly similar to each other, because you're not going to have those weird fluky things that can happen if you take a really small sample. So that is the single best and easiest way to lower your variability, which is a desirable thing. What effect does the population have on the variability of a statistic. So I've got this tub of ice cream that's like this big. It's as big around as this is my population right here. Okay. So this is all my ice cream, and I'm taking like a giant ice cream scoop's worth. We should be fairly like similar in our ice cream scoops when we do it that way. If I take a bucket, maybe we'll be even more similar. But let's say instead of my population being this big, I have like a literal swimming pool filled with this ice cream. And then you and I take our ice cream scoops, or you and I take our buckets. There's not going to be that much of a difference between a population this big and a population this big. You and I are going to get similar answers, no matter if the population is this big or this big. What really matters is the size of our scoop, not so much the size of the container. Okay? So what effect does the sample size of the population have on the variability of a statistic? Not much of an effect. Increasing sample size, definitely. Bigger scoop means we'll be more similar. Increasing size of tub, like this tub is just as good as this tub, like it's not that big of a deal. Okay? So really useful analogy to wrap your head around kind of a hard concept. And we're going to finish off this video with a nice little illustration right here. When you talk about making estimates, you want to estimate the real ACT average in this, or the percent of people with glasses, or whatever you care about. You have two enemies working against you. You have bias and you have variability. Bias and variability are our two enemies when we're making estimates. Bias means we're unfairly favoring one side. We don't want to do that. Variability means we're all over the place. And if we're all over the place, we don't really know what to believe either. So we don't want to be biased, and we don't want a lot of variability. So these pictures over here, the idea is like I'm archery, shooting bows and arrow here at bow and arrows, whatever, at a target, and we're looking at the different possibilities. So I'm aiming for the center of the target right here, which is my parameter. It's what I'm trying to get. On this first picture, I am really consistent. I'm hitting the same spot again and again, but that's not what I'm aiming for. I'm unfairly favoring that top side over there. That is biased, but it's low variability. I'm very consistent, but I'm consistent badly, like in a spot I'm not supposed to be. Okay, so I'm unfairly favoring one side. Moving over to this top right picture here. This picture is not biased. I'm not biased in favoring one side. I'm just not very good at archery when I'm shooting at this target right here. I'm just kind of all over the place. So I have high variability, but I do have low bias. Okay. Then over here, this one I'm just terrible. I can't hit the target. I'm unfairly favoring one side and I'm all over the place. So that's like really not good. And then the goal is what you see in this last picture, having no bias. You're not favoring one side unfairly. And then you have low variability as well. So as we progress this semester, we will always be conscious of making sure we're not being biased and that we're keeping our variability in our statistic as low as we possibly can. And we'll get more in depth with this as things progress.